Welcome back to AI Paper Podcasts. Today we're diving into a really interesting one, I think. It's called Towards a Physics Foundation Model, or GPHYT for short.
Yeah, this one's causing a bit of a stir. It basically asks, can we move past needing a different specialized model for every single physics problem we want to solve?
Right, like the current state of the art, the PINs and neural operators, they're powerful, but finicky.
Exactly. The authors here are pushing for something much bigger. A single generalized model. Think like an LLM, but for physics, something you train once and then it can tackle, well, almost any partial differential equation you throw at it.
A true physics foundation model, a PFM. Okay, so let's try and nail down the key points for like a 1-minute summary. What's the core problem they're hitting head on?
The main issue is that current physics-aware ML models, like PINs or Fourier neural operators, FNOs, they're just too specialized.
You train one for simulating flow around this specific shape under these conditions.
And if you change the shape or the fluid properties or even just the boundary conditions, you basically have to retrain it from scratch. It doesn't generalize well outside its narrow training scope.
Okay, so brittle specialization is the problem. What's the GPHYT solution then?
Their answer is GPHYT. It's this massive single model based on a transformer architecture. And they trained it on a huge data set, 1.8 terabytes of really diverse simulation data.
Whoa, 1.8 terabytes. What kind of data are we talking about?
All sorts. Fluid-solid interactions, shock waves, convection, even complex stuff like multi-phase dynamics and porous media. Real variety.
And the big technical leap, the key idea.
It's in-context learning applied to physics. So GPHT figures out the governing dynamics, the actual physics of the system it's looking at, just by looking at a sequence of prior states, like a prompt.
So you feed it a few frames of how the system evolved.
Exactly. And from that prompt, it infers the rules without you ever explicitly telling it, this is Navier-Stokes, or these are the boundary conditions.
Okay, that's pretty radical for physics simulation.
Yeah.
And did it? Did it work? What were the results?
Yeah, the results are quite striking. It significantly outperformed those specialized architectures, up to 29 times lower median mean squared error in their tests.
29 times.
Yeah. And maybe even more importantly, it showed really promising zero-shot generalization.
Meaning it could handle things it absolutely hadn't seen in training.
Exactly. New boundary conditions, even completely new types of physics, like supersonic flow, which wasn't in the training set at all.
Yeah.
And it still produced physically plausible results. That's the foundation model aspect shining through.
Okay, that's a strong opening pitch. So this PFM vision, it's directly inspired by the success of LLMs, right? That whole train once, deploy anywhere idea.
Absolutely. We see models like PaulM2 or BERT showing these incredible emergent abilities, handling tasks they weren't explicitly trained for. That's the dream for computational physics, too.
But physics seems harder, more constrained by strict laws, but also incredibly diverse in phenomena.
It is harder in many ways. And that's why the current best methods fall short of being truly foundational. Let's talk about PNNs for a second.
Physics-informed neural networks. The idea is neat, you bake the PDE itself into the loss function.
Right, as a soft constraint. It forces the network's output to try and satisfy the known physical laws, minimizing the residual of the PDE, and they're great for the specific problem they're trained on.
But yeah, change the PDE, change the geometry.
And you're back to square one. They don't generalize beyond their specific setup.
Okay, what about the other main approach? Neural operators like FNOs.
FNOs, Fourier neural operators, are different. They try to learn the actual solution operator, the mapping from the input conditions or functions to the output solution function.
Which makes them discretization invariant, right?
Yeah.
That's a big plus. They can handle different mesh resolutions.
Correct. That's a key advantage.
Yeah.
But fundamentally, they're still trained on and limited to a relatively narrow class of physical systems, or PDEs. They don't easily jump from, say, fluid dynamics to heat transfer without retraining or significant changes.
So the core barrier to a true PFM is this sheer diversity of physics. You've got phenomena at vastly different scales, governed by different equations. Microfluidics versus weather forecasting. How does one model learn all that? Plus, getting enough data across all those domains must be incredibly expensive.
That's the crux of it. The diversity is immense, and simulation data is expensive to generate. A PFM can't rely on being explicitly told everything about the system. It has to learn to infer the system dynamics purely from context, from the data it sees in the prompt.
Which brings us to the GPHYT architecture itself. You mentioned it's a transformer, but also a hybrid system, not just a pure neural network.
Right, and that hybrid design seems critical for stability, especially for longer simulations. It's not just predicting the next state directly from the previous ones.
Okay, break that down. What are the components?
So you have two main parts. First, a transformer-based neural differentiator. This is the core learn component. It takes the input prompt, those multiple prior time snapshots of the physical state, and its job is to predict the rate of change of that state over time.
The partial derivative, xs.
Exactly. It learns to approximate that derivative function based on the context provided by the input sequenced SDA.
And how does the transformer actually process this physical field data? It's not text.
They borrow an idea from vision transformers using something called non-overlapping spatiotemporal tubelet patches. Think of it like dividing the input video or sequence of fields into little 3D blocks spanning both space and time.
Okay, tubelets. And then attention works across these tubelets.
Yes, and crucially, they use unified attention across all dimensions, space and time together.
Why is that unified attention so important? Why treat space and time jointly like that?
Because for complex physics, think turbulence or shockwave interactions, the dependencies aren't neatly separable. What happens here spatially affects what happens over there much later in time. A disturbance travels. Unified attention lets the model capture those long-range, non-local, non-separable interactions. It sees the whole spatiotemporal context at once.
Makes sense. And they don't just feed it the raw physical fields like pressure or velocity.
No, they enrich the input. They actually compute first-order spatial derivatives numerically, like Tinksy 2 dolls, and also the time difference to D between snapshots, and concatenate those right onto the input channels along with the raw fields.
Ah, so giving the network a hint about the gradients already present in the data?
Exactly. It's a smart inductive bias. It really helps the model, especially with resolving sharp features like shock fronts, where the gradient information is critical and might be hard to learn quickly from just the raw values.
Okay, so the transformer processes the enriched input using tubelets and unified attention and outputs the predicted time derivative. What's the second part of the hybrid system?
That predicted derivative is then fed into a standard off-the-shelf numerical integrator. Its job is simply to take the current state, zexamarlers, and the predicted rate of change as step forward in time to predict the next state, zexi plus 1.
Interesting. So the heavy lifting, the complex physics learning, is in the neural differentiator, and the time stepping is handled by a classical method. Which integrator did they use? I was expecting something sophisticated like Runge-Kutta.
You'd think so, right. But they actually found through ablation studies that the simplest one, the first-order forward Euler method, worked remarkably well.
Really? Just forward Euler?
Yeah. They compared it to higher-order schemes like RK4 and found that in this hybrid setup, the extra complexity of the integrator didn't bring significant accuracy gains. Forward Euler was computationally cheaper and yielded similar results.
So the power is really concentrated in the transformer's ability to learn that complex derivative function accurately. The specific integrator choice was less critical.
Precisely. It underscores that the learned component is doing the sophisticated part.
Okay, brilliant architecture. But you mentioned that massive 1.8 TB dataset. How do you even curate something like that to teach generalized physics? What was their data strategy?
Well, scale and diversity were key. Over 2.4 million snapshots in total. They pulled from standard benchmarks, things you often see like shear flow, Euler equations, Rayleigh-Benard convection problems.
The usual suspects.
Right. But crucially, they didn't stop there. They added data from more complex engineering-focused simulations, flow around obstacles, thermal flows with heat transfer, even multi-phase flow in porous media.
So introducing things like solid boundaries, different governing equations, phase interactions, really mixing it up.
Exactly, building that diversity. But just having diverse data isn't quite enough to force the in-context learning. They needed specific data augmentations.
Ah, yes. You mentioned this was key to making the model infer rules instead of memorizing scales.
Yeah.
What were those augmentations?
Two main ones. The first is really clever, variable time increments. When creating the training sequences, they didn't use a fixed time step between the snapshots and the prompt, they varied it.
So the time gap between frame 1 and frame 2 might be different from the gap between frame 2 and frame 3 within the same input prompt.
Exactly. Sometimes the snapshots are close together in time, sometimes further apart. This forces the model. It cannot assume a constant time step. It must infer the temporal dynamics, how fast things are changing, from the content of the snapshots themselves.
Making it robust to different sampling frequencies or simulation speeds. Very smart. That was the second one.
Per dataset normalization. Physics operates at vastly different scales, right? Microfluidics versus atmospheric convection. If you normalize everything globally, you lose that scale information.
So they normalized each dataset independently before feeding it into the model.
Yes. This means the absolute values in the input tensors don't have a fixed physical meaning across datasets. The model has to look at the context, the flow patterns, the structures within the prompt to figure out, these numbers likely represent this kind of pressure scale or this velocity scale in this specific physical scenario. It forces scale inference.
Okay, those two augmentations together sound crucial for enabling that in-context learning ability. Let's talk performance then. You mentioned that huge 29x reduction in median MSE compared to specialized models like FNOM. Can you put that into perspective? What does that really mean?
It means that, on average, across a wide range of different physics problems in their test set, GPHE made predictions that were, in terms of squared error, almost 30 times closer to the ground truth simulation than a highly tuned FNO model designed for similar tasks.
That's just incremental. That's a different league.
It really suggests that this transformer-based approach, learning the derivative in context, is fundamentally a more powerful way to capture the underlying physics compared to learning the direct solution operator like FNO does, especially when aiming for generality.
And it wasn't just the big model that did well, right? The efficiency point.
That's also impressive. Their smallest version, GPHYT, had only about 9.2 million parameters. Compare that to the full-sized FNO and UNet models they compared against, which were over 100 million parameters each.
And the small GPHYT still won.
It still outperformed the median MSE of those much larger specialized networks. It really shows the parameter efficiency you get from that spatiotemporal transformer architecture and the unified attention mechanism. It leverages the parameters very effectively.
Okay, numbers are one thing. What about visually? Did the quality of the predictions look better?
Yes, and the qualitative results really show why GPHYT performs better numerically. For smoother flows, like flow around an obstacle, GPHYT, and maybe a good UNet capture the fine details, the small vortices, pretty well. FNO sometimes struggles a bit with precise spatial localization even there.
But the real test is the hard stuff.
Exactly. When you look at systems with sharp gradients or discontinuities, think Euler shock waves, or the complex plumes in Rayleigh-Benard convection, the difference is stark. GPHYT manages to maintain really sharp shock fronts. It tracks the intricate details of the convective plumes accurately.
And FNO?
FNO tends to produce overly smoothed predictions in those cases. It sort of smears out the sharp features. It captures the general flow, maybe, but misses those critical high-frequency details that are often physically very important.
Which really brings us to the heart of the PFM idea, this zero-shot generalization. This is where GPHYT needs to prove it's more than just a good universal approximator, right? It needs to adapt.
Absolutely. This is the make or break test for any model claiming to be foundational. Can it handle genuinely new situations without needing retraining or fine-tuning?
How do they test this?
They did it in 2 stages. First, they tested generalization to new boundary conditions for physics it had seen during training.
Okay, like taking a known flow system but changing how the edges behave.
Precisely. For example, they took the chaotic Euler flow system, which was trained with periodic boundaries, and tested it with new open boundary conditions where mass could flow in or out, something the model had never explicitly encountered for that system.
How the result?
The prediction accuracy, the MSE, was nearly identical to the original periodic system. It handled the unseen boundary condition almost perfectly.
That's quite something. It implies the model learned the core physics, the bulk dynamics, separately from the boundary effects. And it could then infer the new boundary behavior just by observing the flow near the edge in the prompt.
That's the interpretation, yeah. It successfully disentangled the core physics from the specific constraints it was trained on.
Okay, stage 1 passed. What was stage 2? The ultimate test.
Stage 2 was generalizing to entirely novel physics, scenarios involving physical laws or regimes completely absent from the 1.8 TB training set.
Like what?
They used 2 main examples: supersonic flow around an obstacle and a turbulent radiative layer. Neither supersonic effects nor radiation were part of the training data. This is pure extrapolation into the unknown.
Okay, nerve-wracking time for the researchers, I bet. What happened?
Well, as you'd expect, the quantitative error, MSE, was higher here. The model is operating outside its training distribution. It's harder.
But did it completely fail? Or did it capture anything meaningful?
That's the fascinating part. It didn't fail. It still captured the essential dynamics. For the supersonic flow, the most striking thing was that GPHYT correctly formed a bow shock wave in front of the obstacle.
Wow. Even though it had never seen supersonic flow before.
Exactly. It didn't predict the shock with perfect accuracy, the position or sharpness wasn't exact, but the qualitative phenomenon, the formation of a bow shock, emerged correctly. That's strong evidence of genuine generalization, of learning transferable physical principles rather than just memorizing patterns.
That feels like a glimpse of truly emergent behavior like we see in LLMs. Okay, so generalization looks promising, albeit not perfect for totally new physics. What about long-term stability? Simulators need to run for many steps.
Crucial point. A model that's accurate for one step but blows up after 10 is useless. So they tested this with autoregressive rollouts, feeding the model's own prediction back in as input for the next step for up to 50 time steps.
And how did GPHYT hold up over that duration?
Pretty well, actually. It maintained physical plausibility and stability. For complex systems like the Euler shockwaves, it preserved the large-scale structures, the interactions with boundaries, without the simulation diverging or producing nonsensical results over those 50 steps.
That's good. What about for the generalization cases? Did the stability hold when dealing with new boundaries or physics?
Yes, interestingly. When they did rollouts on the Euler system with the new open boundary conditions, the error growth rate over time was almost identical to the rollout with the known periodic boundaries. It suggests the in-context learning wasn't just a one-step trick, it held up consistently over time.
But we need to add a big caveat here, right? Especially for engineers listening who might be thinking about using this tomorrow.
Absolutely. A critical caveat. While GPHT is stable and captures dynamics well, error does still accumulate over these long rollouts. High-frequency details tend to get washed out over time.
So precision.
Precision. The paper is very clear on this point. GPHT time, in its current form, still falls considerably short of the accuracy and precision you get from traditional, dedicated numerical solvers, especially for long simulations. For mission-critical engineering applications where you need extremely high fidelity, we're not quite there yet with this approach.
Okay, so GPHT is a major proof of concept. It shows this foundation model path is viable for physics, using this hybrid transformer and in-context learning, but it's not the final answer yet. What are the main limitations they point out, the big hurdles for future research?
Several key areas. First, it's currently limited to 2D systems. Extending this effectively to 3D is a major computationally intensive next step, though the architecture itself should allow it.
Makes sense. What else?
The breadth of physics covered is still relatively narrow, mostly fluids and some heat transfer. A true PFM would need to incorporate structural mechanics, electromagnetism, chemistry, optics. You know it. Much more physics needs to be integrated.
Expanding the dataset and possibly the architecture.
Right. There's also the limitation of a fixed spatial resolution. It was trained on 256 by 128 grids. Making it resolution independent like neural operators would be beneficial. And perhaps most importantly for practical use, improving that long-term accuracy and precision remains a huge challenge.
So scaling up, broadening the physics scope, handling resolution, and nailing down precision. Lots to do.
Definitely. But the path seems clearer now.
Okay, so wrapping up, we've seen GPHYT learn to infer boundary conditions, even grasp the basics of entirely novel physics like supersonic flow, just from the data patterns in its prompt. It wasn't explicitly programmed with those rules, it learned them implicitly.
Which is the core promise.
So the big question this paper kind of throws out there for all of us, the provocative thought is, what's the limit here? How much physical law can a model like this implicitly learn just from observing enough diverse examples? Could we reach a point where explicitly programming PDEs into our models becomes unnecessary?
And if so, what kind of data corpus, how vast and diverse would it need to be to actually capture that universal physics engine implicitly?
It feels like the door to that possibility is now open, even if the road ahead is long.
It certainly does. A really foundational piece of work.
Absolutely fascinating. Well, that's all the time we have for this AI Paper podcast. Thanks for joining us.
Thank you.